Traditional antibody discovery is a numbers game. Researchers immunize animals or screen massive physical libraries, relying on biological chance to produce a viable therapeutic candidate. This method is limited by the constraints of the laboratory. You can only find variations of protein scaffolds that have already evolved in nature. Modern labs are bypassing these biological constraints by designing entire therapeutic candidates in silico. This process enables the creation of zero-shot antibodies, entirely novel sequences engineered from the ground up that have no prior existence in the natural world. Instead of managing the multi-year timelines of physical screening, researchers use generative models to evaluate thousands of computational variations in days. The shift is driven by the need to target difficult epitopes. These are specific sites on a pathogen where no structural data exists, making them nearly impossible to hit using traditional, scaffold-based methods. Antibody development has evolved into a computational engineering discipline, utilizing a multimodal pipeline to solve these structural challenges. The first requirement of the pipeline is structural, creating a viable 3D protein architecture from scratch. Diffusion models, specifically architectures like RF diffusion, serve as the generative engine for this physical topology. Starting with random noise, these models denoise data, snapping points into a folded protein. Versions like RF antibody isolate flexible CDR loops. Platforms like Origin 1 guide these loops to perfectly match the contours of target epitopes lacking prior structural data. While diffusion determines the 3D shape, the pipeline must still define the underlying amino acid sequence that will hold that shape together chemically. This introduces the second phase, assigning the exact chemical building blocks to the 3D structure. Protein language models, or PLMs, like ESM2 or IgLM, provide the solution for this sequence mapping. These models treat linear amino acid sequences as a language, learning the grammar of how proteins are successfully constructed in nature. The model fills sequence gaps by predicting likely amino acids based on chemical context. Drawing from successful proteins, the PLM selects residues to satisfy the local environment, ensuring an energetically favorable sequence that won't collapse. Combining 3D diffusion and 1D language models creates a stable baseline structure, but the molecule still requires optimization to achieve a therapeutic level of binding strength. To be effective, the candidate must undergo affinity maturation to refine its binding strength with the target. Traditional maturation is an experimental bottleneck, requiring researchers to test thousands of random mutations using physical assays like surface plasmon resonance. Deep learning simulations bypass this brute force testing by analyzing the interface between the antibody and its antigen target. The AI identifies hotspot residues. These are the specific locations where a single point mutation is statistically most likely to increase the strength of the bond. This graph maps mutational steps against binding free energy. As the AI suggests substitutions, the curve drops, representing a more stable physical interaction. Because predictions occurred in silico, months of feedback are compressed into a single computational cycle. This transforms affinity maturation from a trial-and-error search into a targeted optimization function. A molecule with high affinity is only useful if it remains stable during manufacturing and is safe for the patient. Researchers use AlphaFold 3 to validate the design by computationally docking the complex, ensuring the flexible CDR-H3 loops align exactly with the target. Graph neural networks further verify the design by treating the 3D complex as a mathematical graph, mapping the exact interactions of every residue. The sequence then undergoes AI-guided humanization. This graphs the active loops onto compatible human frameworks to ensure the molecule is not flagged as a foreign threat by the patient's immune system. Finally, the candidate enters a developability filter. The AI generates scores for aggregation propensity, viscosity, and thermal stability. Molecules that show a high risk of clumping or breaking down are filtered out. This identifies biophysical liabilities early, before expensive large-scale production. These computational filters ensure that ultimately only the most stable and manufacturable candidates reach the final production phase. While these models are highly predictive, the final validation must still happen in the physical world. To bridge this gap, the industry is moving towards the closed-loop biofoundry. In this system, AI generates over 100,000 candidates. automated synthetic biology platforms then print the DNA and express the physical proteins. This follows a 4-step cycle. In the test phase, hardware measures the binding kinetics of printed proteins. Results are fed back into the AI, which learns from physical discrepancies to improve next designs. This feedback loop creates compounding accuracy, making successive generations more precise. The integration of generative AI and automated foundries allows molecular biology to function as a data-driven engineering cycle, where therapeutic candidates are built through continuous, self-correcting feedback.